In this video, I'd like to talk about using Make to create workflows and to document your work. And Make is a program that when I did some research, I found it was created all the way back in 1976, making it one of the oldest continuously used programs, I think, around. And it was built to help create executable programs from source code files. So originally people were working like in the C language, and this was used to help compile C programs, and I'll show you an example of that in a little bit. But according to the manual, you can use it to describe any task where some files must be updated automatically from others whenever the others change. And so in that way, I would argue that Make has gone far beyond being just a build tool to become something like a workflow system. So I feel like if you can understand Make, then you can understand other kinds of workflow systems, and I give some examples here at the end. So let's just talk a little bit about what a make file does, and I have this illustration here about the idea of maybe creating a lemon meringue pie, and this is a string diagram. I came across this from an introduction to applied category theory, which is something kind of interesting to think about. But the idea here is that these actions, separating the egg, making the lemon filling, filling the crust, making the meringue, all of that, they can be diagrammed out using these string diagrams that show the inputs, these actions, and then the output of those actions following into other actions. And this is, in many ways, what we're trying to do when we're writing workflow systems. Like we're going to take some inputs going to come off the sequencer, and we need to trim and filter those reads and then put them through some sort of identification process. Whatever it is, so whatever is the system, you've got some inputs, they have to go through some transformations, the outputs of those steps go into other steps, and sometimes they are combined in a way. Like for instance here, the egg is separated into yolk and white, and these outputs from separating the egg are combined with other elements to make the lemon filling. And a lot of these things can happen in parallel. So some of these things can happen at the same time, or you could make the crust, the day before and put it in the refrigerator and then pull it out, and it's already sitting there. And as long as you make the lemon filling, as long as the crust exists before you make the lemon filling, then you can put the filling in the crust, and then you can bake it, and then you can add the meringue and all of those kinds of things. So just a kind of a silly idea, but I wanted to come up with a way of maybe perhaps showing this idea of making a lemon meringue pie in with a makefile. And so if you go into the app01 makefiles directory of the GitHub repository, you'll see that there are a few directories here, and I'm going to go into the pie directory. And if we look here, actually I've been running things from before, just testing things here. So I'm going to run something called make clean, and that's going to get rid of the files, and this is what it should look like for you. And I'm going to explain make clean in here in just a minute. And if we look at this, there's this program here called combine. And what it wants is that it's going to create some file, and it's going to put some ingredients in it. And if we look at the way combine is written, there's a little bit of shell, a little bit of bash here that you could learn here, but I'm checking that if the number of arguments to the program is greater than 1, then I'm going to make the file is going to be the first argument, and then I'm going to combine the rest of the arguments and echo those into the file. Otherwise, I'm going to print this usage statement, which is what we've been trying to get from argparse with our Python code. So if I run this, for instance, to combine into a program, into a file called crust.txt, I want to put into there flour, butter, and water. And now if I cat crust, I see here it says it will combine flour, butter, and water. So that's what combine does. That's all it does. And the idea here is that I want to combine different elements to make the parts of the pie, and then combine those things to make the pie and then bake it. And I have here a make file that will do all of this for me. So let's just talk about what this looks like. And I think at some point here, I have a description here of each one of these sections here that are started with a word followed by a colon, and then optionally possibly followed by some other words. And then, so this is called a target. And so the target or a recipe has, it's just a plain word. Oftentimes it will be the name of a file that will be created. For instance, here, filling.txt is going to be the result of running combine to create filling.txt with the lemon butter and the sugar. And meringue.txt is going to be created by combining the meringue into meringue.txt, the egg whites and the sugar. And crust is going to be what we saw earlier. It's going to create crust with flour, butter, and water. Each one of those are considered dependencies to this target called all. And so what all says is that first I need to make sure that the crust exists, that the filling exists, and then the meringue exists. And then I can combine all of those into pie.txt. I can combine crust, filling, and meringue to create that. And then I will cook pie.txt at 375 for 45 minutes. And so that is the basic idea of what's going on here with the make file. And what I'm showing here is that I can make all of this happen by running I can create the filling.txt by saying make filling.txt. So let's try that. Let's go into the pie directory, and if I say make filling.txt, then it will run it is running this command here. And you see here that a target can have more than one command, and they need to be indented here. It's hard to tell, but if I set list on in VI, this is the way that a tab is being shown in my editor. So these need to be indented by tabs, and otherwise I'm just using spaces here like normal on the command line. So set no list there to turn that off. And so I have now created the filling.txt, and I can do the same with meringue.txt. If I say make meringue, and now there is there's a filling. If I cat the filling, and if I cat the meringue, I see that it has indeed done those. And then there's a special target here called clean that doesn't actually create any output. It actually removes files. So if I were to run make clean, it's going to remove all of the text files that would have been created in the course of running this program. And if I look here, it's back to the state of where the program was, of how the repository was when I downloaded it. And so what's going on here is one of the important things here is that if I run with no target at all, it's going to run the first target that it finds. So it's going to run all, and that's pretty common in a makefile, that if you put something as the first target, that's going to be perhaps the most useful, the most used target that you would have. And so if I come in here and I just simply type make is going to look for the existence of a makefile, and without any target, it's going to run the first one that it finds. And that one is going to say, oh, first I need to make the crust, then I need to make the filling, then I need to make the meringue, and then I can combine all those into a pie and then cook it. And so by doing nothing more than typing make, I have executed essentially this program. And this program is really just a bunch of shell commands. So, we're not talking about Python here really at all. We're just talking about, but in the same way that we've written Python programs in this book to create, a bunch of functions that come together to create a program, here we're kind of writing a meta level, another level up above, where we're running a bunch of shell commands, a bunch of which could actually in their own right be programs, and we're running these programs and combining the outputs to create some other outputs, which is, you could write a Python script to do this as well, but make sometimes is all you need. And one of the things I like to do with Make is to use this to document my workflows. What's nice about this is that make files create something called DAGs, which are directed acyclic graphs. And so if we simplify that earlier string diagram into this, we see here that there are 3 inputs that go into py.txt. That needs to be created in order to go to cook.sh. And so once we've created these can happen in any order, but they all need to be satisfied before this step, and then this step needs to be satisfied before this step, and that is a directed acyclic graph. It's directed because there are directions to these arrows. We have to move from the left side of the image to the right side, and there are no cycles. So py.txt does not go back and somehow reference they only go in one direction. So it's a directed acyclic graph. And when you start thinking about graphs, you kind of start seeing them everywhere. I mentioned some sort of an analysis pipeline is basically a graph. Like we take some input, like a FASTA sequence, and then we have some elements to do like trimming, filtering, and such. Maybe that goes into something like blast hits, which we've looked at, or maybe we're looking at gene predictions or some sort of functional annotation. You can actually program a pretty decent workflow just using make and saying, that for instance the trimming action is a prerequisite to some sort of a blasting, and then that is some sort of a prerequisite to something else that's going to and take those blast hits and go into some sort of other program. And so I think it's useful when you're thinking about why do we have make. Maybe it would be useful to simply go use it if it's its intended purpose, which is to compile a C program. So in here there's a C hello program, C hello directory that contains, when you first come in here, it should only contain a hello.c file and a make file. And so let's look at the hello.c. I have it diagrammed out here. Just a little bit of C that you might find interesting to learn. This is sort of like a comment. This is a way of commenting, but it looks like a comment, but this is actually an include, and we're trying to include a header file called standard IO so that we're able to have access to the printf function. This is, we don't need to put function or def in front of function declarations. You actually put the return type before the name of the program of the function name, and we need to have a main function for C to start off the program. It doesn't have to be in a file called main. Here it's in a file called hello.c, which is fine, but often it will be main.c is the place where a program starts, and inside of that it would need to have a main function. I'm showing you here that it doesn't have to be called main.c, but it probably would be. And so we have defined a main. It takes no arguments because it has to get its arguments from the environment. This is a braced language, so the open and closing braces define the block of code that goes for the function called main. And so this indentation is actually not important. C doesn't have to be indented. We do have to end statements in C with a semicolon. And printf works a lot like print in Python. And here we're printing a string, and it's going to have a new line at the end, which is represented here by this \n, which we've seen in Python. And finally, we're going to return 0. So this is something that happens implicitly in our Python programs, but we've seen quite often that when a program runs without errors, it should return 0 to the operating system. That's what's happening here. We're returning 0 to say that the program finished normally, and that's the integer that's being referenced here by the return type. So this is C. I don't want to belabor it too much, but that's essentially why we're writing Python, is so that we don't have to write such low-level code as that. But it is important to understand when you're programming and see that there's two elements here. So you write the code, and the first thing is that you have to compile it, and separately you have to run it. So I can use a program called GCC for the GNU C compiler, and I can compile GCC hello.c. And what that has created, it didn't tell me anything, but it has now created a file called a.out. And if I say, what is a.out, it's telling me it's an executable for my chipset ARM64. And I can now execute a.out, and it says hello world. That's useful, but I don't want it to be called a.out. So there is a second option I can give. There's an option I can give here to GCC saying -o, I want the output to go into hello. And the input for this is going to be hello.c. And now if we look, now there's a hello program, and I can execute it. So that is an element that's the basic idea of how C programs work in a lot of compiled programs. Like I work a lot in Rust. So there's a separate compilation program, separate compilation step, and then I can execute this program as many times as I want. Whereas in Python, generally speaking, all of the compilation and the execution happens all at the same time, every single time, although there can be some caching of bytecode in, sometimes with Python. Anyway, so with that, and rather than having to remember how to type all of this to create my program, I can document all of this in a makefile, which is what I show here. And to start off with here, I'm going to get rid of clean there, and I'm going to show you that there is a hello target here as the first one, and it's going to run that GCC command for me. So if I come in here and let's see, I'm going to go into the C hello directory, and I just type make without any other arguments, it's going to run the first target, and that's C. It's going to execute, it's going to compile hello for me, and now I'm going to have the hello program. And one of the interesting things about make is that if I try to, let me do that again, if I try to execute it again, it's going to tell me that there's nothing to do because hello is already up to date, because it sees that nothing has changed with hello.c. And let me just verify this. If I go into hello.c and I change this to, for instance, hola, and now I type make, well, it's telling me that make is up to date. It doesn't feel like it needs to execute that. So if I type make-b, I'm telling it to go ahead and force it to run all the targets, and now you see it has updated to hola world instead of hello. And so that's a little bit about using make. And here I'm showing that right there. One of the things that I could do if I wanted to always remove the hello file because it didn't want to update because it saw that hello already existed. And this is kind of the point of make, is that when you're compiling a bunch of C files into their object files and then linking them together, you don't want to do that for every single file unless you can tell that it needs to be updated. And so that's part of what make is doing, is that it doesn't want to run these actions when it thinks that the program won't have changed anything. So if I add clean as a prerequisite, as something that has to run before hello, now every time I type make, it's always going to get rid of the executable and recreate it. And it's always going to say hola world now. So that's a little bit about what's going on with make. Something else to note here is that technically, because clean doesn't create anything, it doesn't, like hello here creates the hello target creates the file called hello, which is very typical for how recipes are named. Clean doesn't actually create anything. In fact, it's destructive. And so it's common to list this here as a phony target because it's not actually making anything. And something else to note here is that it would be pretty bad if clean were the first recipe in the file because it's doing something destructive. And so it's very important to me when I'm making make files that clean is usually something somewhere near the end. It's certainly not going to be the first thing it's the first target, because I would probably put something like the all target that's going to do all the actions for me. That would probably be the first one in there. So something to think about. So a lot of the way I have never written C except for that C program. I've always just avoided it. But when I came across make files in the context of actually building software all the time on Unix. I got to understand that I was supposed to download the C code and then run make, and then finally after a while I was like, well, what is make doing? And I looked into make files and I was like, oh, I can use this to just make shortcuts. Like for instance, here if I have this idea of a very, very simple make file where when I say I want to make the target hello, what it's going to do is actually just echo hello world. It's not actually doing anything. It's not doing what in the traditional sense, a makefile target would be doing. It's just executing a bit of shell command for me. And I was like, oh, I could put anything in a makefile, and I can create these dependencies. And so that's how I started getting really excited about using makefiles. They're extremely simple and very straightforward, a way of creating documentation for the work that I do day to day. And so to this day, I've been doing this for years and years. I will come into a project that I haven't seen in months or perhaps years, and I have no idea how to run it. And the first thing I do is look for a makefile. And I usually just go in and just type make, and my program does something. It wouldn't be that useful if we couldn't define variables. And so I'm showing here's an example of a makefile I wrote many years ago to run a program called Centrifuge that makes taxonomic assignments. And these spaces here are not important, but I do put spaces there in my makefiles to make them a little more readable than this would not be allowed in shell. So to a large extent, make looks almost exactly like a shell command. So if I were writing this in bash, I would have to remove these spaces because of the way bash does arguments and all that. But in makefiles, I can have these spaces here, and I dereference them very similarly to how I would do them in shell commands. So in shell, there's this home environmental variable, and in shell I can just say echo home, and on my laptop it's going to be just Youens-Clark. And if I wanted to specify with the brackets, I would use curly brackets, and that is in order to do something like something like that. If I wanted to do this, I wanted to add some sort of extra characters to the end of it, I would need to define where the variable starts and stops. If I didn't have that and I tried to say home underscore xxx, then it would actually be looking for a variable called home underscore xxx, and that doesn't exist. So this is how you do this in shell. In make files, it's very, very similar. It's just we're using parentheses. So I can reference this is a variable here that exists just inside of the make file, but here this is an environmental variable from outside of the make file. So I can use both of these, and I show here that, for instance, if I have this very complex a way of running this Python program I wrote, it has all of these arguments, and I don't want to type that every time I want to run it on some particular data set. So it would be very common for me to have a makefile with lots and lots of targets that document how I ran, for one organism or for some, one data set that somebody gave me. And so this is just a simple way of, I could put all this in a README, but then I would have to copy and paste it out of the README and run it. And it's pretty common for READMEs to become out of date. So I just keep my makefile updated with how I actually ran the programs, and then I don't have to worry about updating my documentation. So I've abused this a little further just to give you something kind of like a real world example. There is this makefile here in the yeast directory that has what a truly maybe kind of going overboard here with trying to show you all the stuff that you could throw into a makefile, but I have essentially a lot of shell commands here that executes this simple workflow, a little program I wrote. I can't remember where I came across the idea, but the goal was to download some data from the internet, from the yeast genome, to download these sequence files, and then to run all these commands to come up with some sort of report of verified genes and uncharacterized genes, terminated genes. And so I wrote this to show you that you could do this. You could put all of this in here, a bunch of shell commands, and then at the end I'm actually running PyTest. And I had to update this with for how it changed since I wrote the book. Some of the numbers have changed, so I did just update this in 2026. So if you were running this earlier, you might have gotten some different numbers because the files changed since the time that I wrote the book. But in the end here, I'm running, you see here, the all command is listed first. And what it just does, after that, it simply lists all the other recipes that need to be run in the order that they need to be run, ending with this test. And the test is running this PyTest, which is looking at, some sort of files. You could read the test.py to see what it's doing. But what's cool about this is that I could, if I go here and I type make clean to get rid of all those files, and I type I want to make the gene count. Well, what gene count has to do is it first has to go get this file called SGD features, and then it's going to create this file called gene count. And now if we count that, we find here that there are 6634 genes here. And if we so if we look at that make file again, I just happen to pick this one out of the middle, and we see here that the first thing, in order for gene count to run, it has to run features. So features went and ran. It says, oh, I need to wget this thing called features. Well, what is features? It is this this variable up here. And without having to manage all that myself, I just simply said, oh, just run the gene count, and it did what it needed. If I were to say run all, when it gets to gene count, it will see that features has already been run, and gene count, in fact, has already been run, and so it won't need to do those again. And so if you understand this, if you can kind of wrap your head around how I am very much abusing make to do something it was not designed to do, then you really understand the basic idea of things called like snake make. And now you probably understand why it has make in the name of it. It's because it's taking basic concepts of make and executing it with Python, which is where we get the snake. So snake make is combination of Python and make. There's something called Common Workflow Language, or CWL, and you define the workflows and stuff in YAML instead of, YAML is yet another markup language. It looks a lot like a makefile, really, with the indentation and such. And there are tools like CWL tool, CWL runner that will execute that YAML, but essentially you're still creating a DAG. You can also do the same thing with workflow description language, WDL. There's something called the Cromwell engine that they have that will execute WDL. And then there's actually another project out of Rust called Sprocket that will execute WDL and do a lot of cool things with WDL for you. Pegasus is something that actually allows you to write Python code to describe a workflow. That is written to an XML file, and then that goes into the Pegasus engine to actually run it. And finally, I mentioned Nextflow here is actually written in a full programming language called Groovy, which is sort of like Java, and that is executed by the Nextflow engine. But all of them have the same basic understanding of some sort of a directed acyclic graph as make. So if you can understand make and you can use that, then I think you could learn any of these other workflow languages and execute them well. And I would also mention there's a Rust version of make called Just, which I think is a little easier to use. But since the book here I was just talking about make, I would first encourage you to go learn a little bit about make. I have a couple of links here to some manuals and some other good books. I don't actually think it's necessary to really understand make. I think if you can understand something as simple as this, then you can understand all that you need to from make, and perhaps you would move on quickly from make to something else like Nextflow or WDL. Anyway, make is